Okay, let's begin. So recall that yesterday we proved the soundness theorem. Yeah, we proved actually the version 2 of soundness theorem. Version 2 states that if T can be deduced from S, then T is a logical consequence of S. And the version 1, which we did not state but I am stating now, says that if S is satisfiable, then S is consistent. Completeness theorem is the harder part out of this duo, and it is the converse of it. So now completeness theorem version 1 is what we are proving right now. We are saying that if S is consistent, then S is satisfiable. There is of course a version 2, and that will be a tutorial problem to show that these versions are equivalent. Yeah, so if T is a logical consequence, then T has a proof from S. Yeah, there is a formal proof. And we have proved, we have completed the proof of step 1 of the proof of completeness theorem version 1. We showed yesterday using what? That if S is consistent, then there is a maximally consistent extension of S. What did we use? Zorn's lemma. Okay. And our job today is to prove step 2. And step 2 is the construction of valuation. Yeah, we need a valuation. We need to show that S is satisfiable. Yeah, so S is satisfiable means there is a valuation V which precisely which satisfies S. So step 2, okay, step 2 says that define a valuation V from SL to true false by V of a formula S is true if and only if S belongs to T naught. So T naught is the maximally consistent extension that we obtained from step 1, and now we are claiming this. Now just a quick recap of the definition of a valuation. In how many ways can you define a valuation? Two ways. The first one is definition on SL, and the second one is just definition on L. Now the second one is very easy to define, right? For definition on L, what do? We just take any arbitrary function to every propositional variable we assign either true or false, and then we extend it in a unique fashion. Whereas here we have to do a bit more work. Yeah, here it is a function from SL to true false which satisfies certain properties. What are those properties? It preserves conjunction and negation. That was in the original setup. Now we are, what is our adequate set of connectives? Implication and negation. So for negation, what do we need to show? Yes, so the valuation of negation T is false if and only if valuation of T is true. Okay. And what should we prove for implication? Valuation of an implication T1 implies T2 is true if and only if either valuation of T1 is false or valuation of T2 is true. Now something like valuation is true has to be replaced by this. Okay, so we are supposed to prove something. So let me write down a bunch of claims. So claim 1, I am going to leave some space for now. Claim 2, we are going to prove 3 claims, and after that we are done. So claim 2, for each T in SL, okay, T belongs to T naught if and only if negation T does not belong to T naught. Now quickly observe T belongs to T naught. What does that mean according to the definition? V of T is true if and only if V of negation T is okay. So now it makes sense, yeah, whatever we are doing. So this is just proving thing for negation, and claim 3 would be for S and T in SL, S implies T, this particular formula is in T naught if and only if what should happen? S doesn't belong to T naught or T belongs to T naught. Yeah, let's just write down the green version again. So V of S implies T is true if and only if V of S is false or V of T is true. But before we prove these two claims, we need some very strong observation. This observation I can say in simple words that T naught is a complete theory. So T naught is a theory. Yeah, I mean theory is a consistent set of formulas. T naught is maximally consistent. So maximally consistent actually means it is a complete theory. It's as good as an ultra filter. And let us see what we mean. So it says that V of it doesn't have to be about V. It says that, I think I used a wrong terminology. I should not use complete theory. T naught is deductively closed. T naught is deductively closed means that for U in T naught, for U in SL, not in T naught, U belongs to T naught if and only if there is a proof of U from T naught. So one part of claim 1 is obvious. Which part is that? If U belongs to T naught, then there is a proof of U from T naught. Why? NLA. Good. So let us prove claim 1. So if U belongs to T naught, then T proves U naught. It's just a one-step proof. It's NLA. Okay. Now the converse is what we are looking for. That is the definition of being deductively closed. Deductively closed means whatever you can conclude from it, you have already included it. Whatever you can deduce from it, it's closed under all its deductions. Okay. So yes, so this is our direct implication, and for the reverse implication we have to do some work. So suppose U can be deduced from T naught, then what can we say? Let us prove it using contradiction. Not contradiction, contrapositive. Suppose U does not belong to T naught. If u doesn't belong to T naught, then what can you say? T naught was what from previous slide? T naught was maximally consistent. Maximally consistent means it is saturated. Yeah, if you add something else to it, then it will explode. So something which is not in it, if you add something which is not in it, then it will explode. Explode means it will be inconsistent. So then by maximality of the consistent set T naught union U, what can you say about this? Yes, this is inconsistent. Okay, then now that we have obtained this, does this remind you of any lemma that we proved last time? So, T naught union U is inconsistent if and only if by lemma 8 T naught proves negation U. Okay, good. Okay, now then what? If, yeah, so now we are going to claim that negation U belongs to T naught. Yeah, so claim, now claim inside a claim. Yeah, but this is a very simple claim. So negation U belongs to T naught. If not, then what will happen? Oh, just give me a moment. That's not what we are, sorry? No, we have to use lemma 9. So maybe I am not writing the claim properly. What does lemma 9 state? If T naught proves U,
and T naught proves negation U, then
yes, okay. So I don't need a claim. So recall that if T naught proves U and T naught proves negation U, then by lemma 9 T naught is inconsistent. Now we are already given one part. T naught proves negation U, that is given. So if T naught proves U, then what will we obtain? That T naught is inconsistent, but we know T naught is consistent. So therefore T naught doesn't prove U. If these two things are true, then T naught will be inconsistent. One of them we know is true, so the second one has to be false. So therefore T naught doesn't prove U, and that's precisely what we wanted to show. Yeah, U was assumed to be not in T naught, and then we showed that there is no proof of U from T naught. Okay, so claim 1 is done. Yeah, so whatever you can prove, it already belongs. It's deductively closed. Okay, so now let us try to prove claim 2. So claim 2. So suppose, okay, so it's a two-part thing again. T belongs to T naught if and only if negation T is not in T naught. Okay, any ideas how to proceed? What if both of them happen? Then T naught is inconsistent. Why? See, if for some T in SL, both T belongs to T naught and negation T belongs to T naught, then by claim 1, I mean claim 1 is both ways. Then by claim 1, T naught will deduce T and T naught will also deduce negation T. And hence, T naught is inconsistent by lemma 9. Okay, so therefore both of them cannot belong simultaneously. At least one of them doesn't belong. So now we have to show that if one doesn't belong, then the second one must belong. Okay, so let us try to show that. So if T is not in T naught, then what will happen? If something is not in a maximally consistent set, then T naught union singleton T is inconsistent by maximality of T naught. Okay, then what is the next step? Then T naught proves. Therefore T naught proves negation T, and which lemma is that? By lemma 8. And therefore negation T belongs to T naught, and that is by claim 1. Okay, so we have proved what we needed. It's simple. If T is in T naught, then we are done already. If T is in T naught, one of them must belong. That's claim 2. Yeah, I mean T belongs to T naught if and only if the other one doesn't belong. So we have already shown that both of them cannot belong. So we just had to prove that if T doesn't belong, then negation T does belong. We are done. So claim 2 is done. Now finally claim 3. Okay. So again, that is if and only if. Let me remind you what the statement is. It says that this implication, conditional implication S implies T belongs if and only if either the first one doesn't belong or the second one belongs. Okay, so we are trying to show the forward implication now. Yeah. So suppose S implies, we'll prove it by contrapositive. So suppose S belongs to T naught and T doesn't belong to T naught. Then what will happen? If T doesn't belong, then what can we conclude? So by claim 2, it suffices to show that negation of S implies T belongs to T naught. We want to show that S implies T doesn't belong to T naught. So by claim 2, it is sufficient to show that its negation does belong to T naught. Okay, so how do we go about this? Lemma? Lemma 6, very good. How do you use lemma 6? MP twice, okay. So you want to conclude from T naught, okay. Don't write anything, just observe. Yeah. So lemma, you want to conclude this as the final line. And what is lemma 6? S implies negation, T implies negation, S implies T, and this is all in bracket. So this is lemma 6. But we also need monotonicity. Because we need T naught on this side. That is monotonicity. Then from there, we need to, the middle step will obviously be one application of MP. Yeah, and that application will give us this. This is MP. And the second application of MP, and we have to have first two lines. What two lines? To eliminate this S and to eliminate this negation T. So T naught proves S. Yeah, that's NLA. And T naught proves negation T. What is that? Claim 2. Claim 2 and hypothesis that T is not in T naught. So easy enough. That's why we proved lemma 6. Yeah, just for this particular step. Well, I should correct. That's why we stated lemma 6. We haven't yet proved. Okay, so this is one side. The second side is, again there are, we'll use contrapositive of the second side. Okay, I'm changing the slide now. Okay. So if S is not in T naught, yeah, that's what we need to show. S is not in T naught, or I mean under both conditions we need this. Okay. So if S is not in T naught, then what can you conclude from claim 2? Negation S is in T naught by claim 2, and what else? By claim 1, T naught proves negation S by claim 1. Okay. And also we are assuming this T belongs to T naught. We are not using contrapositive, and since T belongs to T naught, T naught also proves T. Okay, and what do we need to prove? We need to prove that S implies T is in T naught. So which lemma should we use? Where can you see S implies T? Lemma 3. Okay, so what is lemma 3 saying? So lemma 3, let me write down. Lemma 3 says that negation S implies S implies T. Okay, that is lemma 3. And monotonicity. By monotonicity we can increase the left hand side to T naught. Then because we have S implies T, okay. So this is by MP, provided we say that T naught proves negation S, which we already had. Okay. Now What is the final step? Therefore, S implies T belongs to T naught by claim 1. I think I'm missing something. Yes, okay. Okay. So let me erase this second line. Second line is not relevant. We have to show, observe here that we have to show either this or this. Under any of these assumptions, we have to conclude that S implies T is in T naught. So right now we are just assuming this and proving that S implies T is in T naught. Okay, so let me erase this. So in this first case we have done this. Now there is second subcase. If T belongs to T naught, then T naught proves T, NLA. And then how do I obtain S implies T? Any idea? LA1. So this is T implies S implies T, this is LA1, and then T naught proves S implies T, that is MP. Right, so under both conditions we have shown that, and then again, therefore S implies T belongs to T naught by claim 1. So we completed the proof, but we still need to show one more thing. And what is that thing? We have to say something. Since this is adequate, we have shown from claims 2 and 3 that V naught is indeed a valuation. V. No, we did not use V naught. Perhaps, yeah, we just use V. So V is indeed a valuation. And therefore our proof of complete, and one more line, not done yet. Now clearly V of T naught is true. Yeah, because that's how we defined the valuation. And since S is a subset of T naught, V models S. Yeah, V of capital S is true. So this completes the proof of the completeness theorem. Any questions? If you look at this proof carefully, then it's quite simple. The first step is just Zorn's lemma, which is very standard. This is your first course in which you are looking at Zorn's lemma, so maybe that's why you find it a bit hard. But once you start seeing it in different courses, different subjects, then it will be the same grind, always the same grind. Yeah, Zorn's lemma has the same flavor wherever you go, in whatever field of mathematics. And step 2 is, once we know what we are supposed to do, then it is easy to do it. The only hard part here is to come up with those lemmas. Lemma 7, 8, 9 I would strongly recommend you to remember. Yeah. The other ones, if you need them, I will provide. Okay. So one thing I want to talk about over here, that soundness and completeness, yeah, these two statements are about this proof system. Okay, let me write it. So this is a remark. Soundness and completeness, which are converses of each other, are about the proof system or proof calculus. I mean the one that we followed, what is it called? Hilbert style proof calculus. So it says that whatever axiom schema we took and whatever rules of inference we chose, they are sufficient to describe our understanding. Our understanding means semantics. Yeah, that's what these statements show, all these four statements. Whatever we wanted to capture, we were successful. Yeah, we did not write down any nonsense rules or any nonsense axioms. That is soundness. And whatever we did, that was sufficient to describe everything we wanted to describe. That is completeness. Okay, so completeness theorem is all about a proof system. Whereas incompleteness theorem, which we'll see at the end of the course, very last lecture, that is all about completeness of a theory, incompleteness of a theory. Okay, so we have finished the proof of this